let's say we're dealing with this circuit that has a battery of 48 volts and a capacitor with 4 farads of capacitance and a resistor with 8 ohms of resistance. And I've set it up where there's a loop, a possible loop that has the battery and the capacitor and the resistor, and another possible loop that has just the capacitor and resistor, depending on which way we flip a switch. So let's say we have a switch that can go either of essentially 3 ways. We can have it not connected at all, we can have it connecting the left loop, or we can have it connecting the right loop. Because that's really all a switch is. A switch is just a movable bit of wire that we can use to modify which pieces are connected and which pieces aren't. So let's say to begin with, at a time we're going to call time 0, we connect these. So we connect the switch over to here. What's going to start happening? Yeah, the battery is going to charge the capacitor. Because we now have a complete loop with a battery and a capacitor and a resistor. So that means current's going to start flowing, and since current is just the motion of charge, that means charge is going to start to build up on the plates of the capacitor. We can expect current to flow from a high voltage zone to a low voltage zone through the resistor. So let's start mapping out voltages. We know that, let's say we call the negative terminal of the battery 0 volts. So this entire region would be all at 0 volts, all the way up to the resistor itself. But then what would the voltage be on the other side of the battery? Yeah, we get a plus 48, so the other side of the battery is now at 48 volts, which means this entire region is now all at 48 volts, all the way up to the capacitor. But if the capacitor is empty, what's the delta voltage on the capacitor if the capacitor is empty? Right, no voltage at all. The delta voltage on a capacitor in general is negative Q over C. So if the charge is 0, if it has not accumulated any charge yet, if it starts off empty, then the delta voltage of the capacitor is 0. So the other side of the capacitor will be the same voltage, the same 48 volts, which means how much voltage is the resistor getting? What's the difference in voltage from one side of the resistor to the other? Yeah, 48 volts. So the delta V on the resistor, using the usual negative IR, we know now that the resistor is getting the full negative 48 volts, negative 48 because it starts at 48, ends at 0, equals negative I times R, resistance being 8 ohms. So what can we now solve for? Yeah, we can solve for the current. Divide both sides by negative 8 ohms. 48 divided by 8 would be 6. So we get 6, and then volts over ohms is amps. So that means we have 6 amps of current through the resistor right now. Of course, that's not going to last because as soon as current starts flowing, the capacitor starts charging up. And if the capacitor's charge is no longer 0, that means the capacitor now has voltage. So let's say the capacitor charges up to a certain amount. Let's say the capacitor gets some charge on it. Other way around. The plate most directly in contact with the positive terminal of the battery accumulates positive charge. The plate most directly in contact with the negative terminal will accumulate negative charge. And let's say the capacitor, current's flowing pretty fast. We've got 6 amps of current. 6 amps means 6 coulombs flowing per second. Let's say we wait approximately 1 second until there is 6 coulombs accumulated. Suppose we wait long enough that the charge is now 6 coulombs. If the charge is now 6 coulombs, what would be the delta voltage of the capacitor? Yeah, if we take Q over C, 6 coulombs divided by 4 farads, 6 coulombs over 4 farads, that's negative 1.5 volts, because farads is volts per coulomb, so the coulombs can't, or coulombs per volt, so the coulombs cancel out, we get volts. So that means now with the capacitor charged to, let's say, 6 coulombs, and this is kind of arbitrary, just assuming we're waiting long enough that the new charge is 6 coulombs. Now the capacitor has a delta voltage, specifically a delta voltage of negative 1.5 volts. So that means as you go through the capacitor, you're losing 1.5 volts. So this zone should be 48 minus 1.5, that's going to be 46.5. So now this region in between the capacitor and the resistor is now at a slightly lower voltage. The resistor still has a voltage difference, but that voltage difference is now smaller. Instead of taking 48 divided by 8, we're going to take 46.5 divided by 8. What does that tell you about the new current? Yeah, current's going to decrease. So as the charge builds up on the capacitor, there's more and more voltage difference across the capacitor, which means less and less voltage difference across the resistor. Because the total still has to be, the total of both of those together still has to be a drop of 48 volts overall. These are in series, so they have to split up the available voltage. Overall, the capacitor and the resistor takes the voltage from 48 down to 0. But at the beginning, none of that is the capacitor because the capacitor is empty. All 48 volts go to the resistor. And lots of voltage on a resistor means lots of current flowing. But eventually, as the capacitor fills up, there's more and more charge on the capacitor. And more charge on a capacitor means the capacitor is getting more and more of the voltage. And there's still only 48 volts available. So as the capacitor is getting more and more of the voltage, there's less and less of that 48 volt share available for the resistor. And of course, less voltage on the resistor means less current will flow, a slower current. So the current gets slower and slower and slower, eventually approaching what final result? What would the current be after a long time? Yeah, eventually we have no current on the resistor. And if the resistor has no current, what does that tell you about the voltage difference of the resistor? Also no voltage difference, right? 0 current means 0 delta voltage. So if we wait long enough for the capacitor to be much more full, and we wait long enough for the resistor to have no current at all, if we wait until the current dies off to a complete stop, that means the resistor gets no difference in voltage. The voltage before and after the resistor should be the same. We were already defining the location right before the battery to be 0 volts. So the voltage on the other side of the resistor has to be that same 0 volts if the resistor has no delta voltage. Which means now how much voltage is the capacitor getting? Yeah, the capacitor is now getting the full 48 volts. At the beginning, when the capacitor was empty, the resistor was getting the full voltage of the battery. But now when the capacitor is full in the sense that current has stopped, now the capacitor is getting the full voltage of the battery. And lots of voltage on the capacitor means lots of charge is being stored. Essentially, the 48 volts of the battery is able to do two things here. Voltage applied to the resistor makes current flow. Voltage applied to the capacitor makes charge be stored. So you can do, with 48 volts available, you can have lots of current flowing, but very little charge stored. Or you can have lots of charge stored, but very little current flowing, or maybe some of each. But you can't have lots of each. You can't have lots of current and lots of charge. And you also can't have no current and no charge. You've got to have these add up to 48 volts. So eventually the current will be at a dead stop and the voltage on the capacitor will be the full 48 volts. In that case, if we have 48 volts of voltage, how would you solve for the final charge if we know the voltage? Yeah, if we just multiply by 4 farads, the capacitance, because charge is going to be if we multiply both sides by negative C times delta V. And we know the capacitance here is 4 farads, that's given. And the voltage, we're assuming the capacitor is now getting the full 48 volts. It's a voltage drop from 48 to 0. So that'll be negative 48. The negatives cancel out, and we get 4 times 48, so that'll be 192, I think. So 192 coulombs would be the charge on that capacitor after a long time. Any questions on that so far?
Casey, can you explain one more time how you know that eventually it becomes the full 48 on the capacitor, and like why that's different from at first it was not the full 48?
Right. At the beginning, the resistor was getting the full 48 volts because the capacitor was empty. But after a long time, the current has gotten slower and slower and slower and slower. What's the slowest the current could become?
0.
Right. So eventually we expect the current to get slower and slower, approaching 0. And that's because the resistor is no longer getting any voltage. Instead, the capacitor is getting all the voltage. And again, okay, since these are in series, they add up their voltages. They have to split up the available voltage.
Okay, thank you.
Mm-hmm. You can also see this from the loop rule. If you write out the loop rule for this entire loop, we've got voltage of the battery. We got a delta voltage for the capacitor. We've got a delta voltage for the resistor. That forms a complete loop. So what do those have to add up to? Yeah, those have to add up to 0. How do we know when charge is negative or positive? Charge being negative or positive is really just about which plate has the positive charge and which plate has the negative charge. I think in most cases you can just treat charge as an absolute value in this case, because one of the plates is going to have positive charge, one has negative charge. Specifically, if you're in the process of charging it up, the plate most directly connected to the positive terminal of the battery will eventually accumulate positive charge. The plate most directly connected to the negative terminal will accumulate negative charge. Or if it's discharging, you would expect the charge to flow out. So eventually both plates would approach no charge at all. But also in general for a capacitor, the plate that has positive charge is going to be associated with higher voltage. The plate that has negative charge will be associated with lower voltage. So anytime you've got a capacitor that has charge on it, let's say you've got positive charge on one side, negative charge on the other side. The plate with negative charge will be at low voltage. The plate with positive charge will be at high voltage. Relative to each other. The actual difference is going to depend on the charge, of course, the amount of charge. But in general, the positive plate will have higher voltage and the negative plate will have lower voltage because the charge is what's causing the voltage difference here. Any other questions on that so far? Likewise for any resistor. For any resistor, which direction should you expect current to flow? Yeah, from high voltage to low voltage. So in a resistor, if you know which direction current is flowing, then you know where the voltages are. You know that you've got high voltage on the place that current is flowing away from, and low voltage in the region where current is flowing towards. So those rules should be universal. Anytime you've got a capacitor that has charge on it, the positively charged plate is going to be at a higher voltage and the negatively charged plate is going to be at a lower voltage, no matter what. And anytime you've got current flowing through a resistor, the side of the resistor that current is flowing from is going to be higher voltage, and the side that is flowing towards is going to be lower voltage. That also is universally true. Likewise, for a battery, the terminal called positive is at a higher voltage. The terminal called negative is at lower voltage. because all of these circuit elements can be thought of as providing a delta voltage, a difference in voltage. The amount of difference in voltage depends on things like the current and the charge, but which side is high voltage and which side is low voltage is very predictable. Any questions on that so far? How do we find the delta V capacitor after a long time? In this case, after a long time, we can actually go back to the loop rule. One way is to just say that after a long time, there's no current, so the resistor has no voltage. So this voltage and this voltage are the same. So this entire zone, including both sides of the resistor, is all at 0 volts. This entire zone is all at 48 volts. So you can see that the voltage on one side of the capacitor is 48, on the other side is 0. So the difference is negative 48 volts, final minus initial. In this case, the current would be flowing, if you take a look at before this, like let's say the voltage hasn't dropped all the way or the current hasn't dropped all the way to 0 yet. Let's say we've just gone halfway. So let's say we're at a halfway point where the capacitor is getting half the voltage and the resistor is getting the other half of the voltage. Once again, we should expect current to flow from the high voltage zone towards the low voltage zone. 24 volts is higher than 0 volts, so we expect current to flow through the resistor from high voltage to low voltage. And then it's going to circulate around the rest of the loop that same direction. So current is going to flow clockwise in this case as the capacitor charges up. And we can also take a look at this in terms of the loop rule. We can say delta voltage of the battery is always going to be plus epsilon. Delta V of the capacitor is always going to be negative Q over C. Delta V of the resistor is always going to be negative IR. And I find it useful to add these terms to the other side just to simplify things a bit. When do we use plus Q over C? Formally, I would always use negative Q over C, actually. The delta voltage for a capacitor should always be negative Q over C. But the negative is really just talking about direction anyway. Mathematically, though, it should always be negative. And that negative ultimately signifies the direction it's trying to push. The capacitor is trying to push current in a direction that removes charge from itself. Like in this case, the battery is trying to push more charge into the capacitor. The capacitor is pushing back. The capacitor is trying to block or prevent charge from entering itself. So we treat that as a negative voltage in the sense that it's trying to act against more charge getting into itself. Even if you're discharging the capacitor is pushing in a direction trying to remove charge from itself. That removal is a negative change. So the delta V for the capacitor should be negative Q over C in the sense that it's acting against more charge. If we add these terms to both sides, though, add Q over C to both sides, add IR to both sides, we get epsilon equals IR plus Q over C. And I think this modified form of the loop rule can often be more useful for interpreting what's going on. Because you could think of this as the voltage of the battery is split up amongst the resistor and the capacitor. Just like what we were saying earlier, the capacitor gets some share of the 48 volts, the resistor gets the rest of the 48 volts. They have to split up the available voltage. So the 48 volts can cause lots of current and only a little bit of stored charge, or lots of stored charge or only a little bit of current, or in this case, some of each, if we're splitting up the voltage evenly. But of course, that split up is going to change as time passes. In fact, it can be very useful to look at what's going on very early and very late. Like if we take a look at what's going on at time 0, when the capacitor was empty. You plug in 0 for Q in this equation and what's left? What do we still have if we assume charge is 0? Yeah, just epsilon equals IR. So this is the modified loop rule when the charge happens to be 0, which means we can then solve for current and get epsilon over R. So that would be the initial current. Let's say I sub 0, the current at time 0. In this case, epsilon over R, that's 48 over 8, so that will be 6 amps. And notice that this is the same 6 amps we got earlier by mapping out the voltage. The loop rule is doing the exact same thing as mapping out the voltage, is just a different way of portraying the mathematics. And note that this is basically what we'd get if there was no capacitor. If there was no capacitor at all, if it was just a loop with a battery and a resistor, this is exactly the result we would get. So one way to think of this is that an empty capacitor acts like just wire. Because for an empty capacitor, Q over C is 0, and a wire also has 0 voltage difference. So anytime you've got an empty capacitor, you can redraw the circuit at that instant by treating the capacitor as just wire. You can say that this circuit is going to act like just battery and resistor at this instant. And of course, that immediately starts changing. As soon as the capacitor gets any charge at all, then that's no longer true. But an empty capacitor at that instant acts like just wire. We sometimes say it acts like a short circuit in the sense that it acts like these points are directly connected. But of course, that starts changing as soon as the capacitor begins to charge up. In fact, if we take a look at that, if we say after a long time, and formally that means we're taking the limit as t goes to infinity. But in practice, we really can just consider this as after a few seconds or after a few minutes. These processes tend to happen very fast. So after a long time, we should expect the capacitor is so full that what happens? Yeah, we should assume that IR is 0, because the fullest the capacitor can possibly get is if there's no current left at all. If the current stops flowing, then all the voltage of the battery goes into making charge get stored or keeping charge stored. So if we assume that current is eventually 0, or at least current is almost 0, mathematically it's going to be an asymptote. It never truly reaches 0, but it gets close enough. Then our new loop rule is epsilon equals Q over C, because all the voltage of the battery goes into storing charge in the capacitor. And then we can solve for charge. We usually call this Q max or Q final because it's the maximum charge it stores after a long time. Multiply both sides by C. And capacitance times epsilon, the capacitance of the capacitor times the voltage of the battery, tells you how much charge it stores after a long time. And this is the same as what we calculated earlier. 4 farads times 48 volts, 192 coulombs. Again, same process, ultimately just a different way of writing out the mathematics. Either mapping out the voltages in the loop or writing out the loop rule and running the numbers there. Same result, just different ways of looking at it. Any other questions on that so far? Then let's try graphing this. We know some stuff about what's going on at time 0 and also after a long time. Those are really the two most important things to look at, I think, for any situation where you know is going to be exponential decay. Ask yourself, what's happening at the very beginning? That gives you a point on the graph. And what's happening after a long time? That tells you the asymptote that everything's approaching. So now that we know those values, let's try graphing this out. Let's try making a graph of both charge and current on two separate graphs, because they're different quantities, so we can't really put them on the same axis. But let's say we have a graph of time versus current. And that's going to start at 6 amps. So I'll put 6 amps at the top. And then let's also make a graph of charge. And we know that's eventually going to reach 192 coulombs, so I'll put 192 coulombs at the top. Whereas for simplicity, let me just mark it in, I don't know, 25s or something. So we start just a little bit below 200. Or no, sorry, we don't start at 200. We start at 0. Because we start with the capacitor empty. But we know we're going to approach an asymptote just below 200. All right, so what do we know is going to happen to charge or to current? Current starts off at 6. What's going to happen to it? Yeah, it should decrease. And since we should expect exponential decay here, it's going to decrease quickly at first, and then slower and slower and slower, leveling off to 0. Meanwhile, what's going to happen to the charge? Yeah, charge is going to increase, and it'll increase quickly at first because current is flowing quickly. But then as we get weaker current, we get a slower change in charge, because weaker current means the charge increases more slowly. In fact, since current is just the derivative of charge, we can say that at any instant in time, the value of current tells you the slope of charge. Value of current tells you the slope of the charge graph. And since current's getting closer to 0, the charge graph gets closer and closer to 0 slope. Gets closer and closer to flat. And note that these both count as exponential decay. Even though charge is increasing, it's approaching some asymptote. So the difference between the value and the asymptote, that difference is getting smaller and smaller and smaller. So that difference is what's decaying. Any questions on that so far? So we know the starting point and the asymptote for both of these. The one thing we haven't really delved into very much is how long it takes. Because maybe the current decays like this, maybe it decays much more gradually, maybe it decays much more quickly. What's going to make the difference between how fast it decays towards the asymptote? What determines how quickly it approaches the asymptote? Or how would you measure like how much time it takes to decay a certain amount? What are the usual terms we use to describe the amount of time it takes to decay to a certain fraction of the original? Yeah, the idea of half-life and time constant, right? So let's try evaluating those as well. If we can figure out the half-life and or the time constant, we can pinpoint how quickly it decays much more precisely. So let's try that. We'll keep the starting point and the asymptote for both of these, but let's see if we can find the half-life and or time constant to get more detail, more accuracy about how quickly it decays. Anyone happen to remember how to calculate half-life and or time constant for a circuit with a resistor and a capacitor? What's going to determine how long it takes to decay to half the original or to 1/e of the original? This is generally called an RC circuit if you have just one resistor, one capacitor in a single loop, and optional, so everything in series, and optionally with a battery as well. Or alternatively, if you've got a more complicated circuit, as long as you can simplify all the resistors to just one big resistor, and possibly many capacitors, but they can all be simplified to just one big capacitor. We call that an RC circuit, and this turns out to be very predictable. It turns out that the time constant ends up just being R times C, the resistance times the capacitance. Because if you multiply those together, coulombs times farads, and simplify the units, it ends up just being seconds. Coulombs times farads equals seconds. And then the half-life is just going to be, we usually write that as capital T sub 1/2. That's just the time constant times logarithm of 2, specifically natural logarithm. In other words, R times C times natural logarithm of 2. The idea is that in the exponential decay function, whether it's for current or for charge, is always going to have an e to the negative T over RC in it, if you're dealing with one resistor and one capacitor. And if you plug in RC for T, what do you get if you just replace T with RC? What's going to happen there? What does that exponent become if T is replaced with RC? Yeah, you just get e to the negative 1, which is 1 over e. So if T is RC, if T is the time constant, then this whole thing just becomes 1 over e. So that means at that time, at time RC, you'll get 1 over e of the original amount. Or if you plug in RC ln2, the RC's cancel out, you're left with e to the negative ln2. What's e to the power of natural logarithm of 2? Ignoring the negative for the moment, what's e to the power of logarithm of 2? Yeah, that's just 2, right? The e to the power of and the logarithm of cancel out. And then the negative in the exponent just means take the reciprocal. So that means e to the negative T over RC becomes exactly 1/2 if T is RC times logarithm of 2. So this is really why these work, because the exponential decay function is going to have e to the negative T over RC in it. If you plug in RC for T, you just get e to the negative 1, which is 1 over e. If you plug in RC times logarithm of 2, the RC's cancel out, you get e to the negative logarithm of 2, which is 1/2. So we can use these, if we can calculate these times, we can use those to graph these graphs in much more detail. So let's try that. R times C is going to be 4 times 8, which is 32. And again, this is going to be in seconds. Coulombs times farads is seconds. And then if we take that same R times C, that same 32 seconds, and multiply by logarithm of 2, that should tell us the half-life. 32 times logarithm of 2, about 22.2. So that means every 32 seconds, the value drops to 1 over e, about 37% of what it was before. Nothing particularly special about 37%. It's just that 1 over e is a convenient reference point. Likewise, every 22.2 seconds, the amount drops to half of what it was before. So let's try putting this on the graph. Let's say we take this out to maybe 100. Let's try going out to 100. And you can do a little bit of that. There we go. So each of these tick marks represents 10. And when we put the exact same scale on the other graph, so we can compare them. So every 32 seconds, we should expect the amount to drop to 1 over e of what it was. And also every 22.2 seconds, we should expect the amount to drop to 1/2 of what it was. So let's try the half-life first. Every 22.2 seconds. So let's say 22.2 and 44.4, 66.6, 88.8, and then the next one will be off the graph. But every one of these gaps should be correlated to dropping halfway, halfway, halfway. And we could do the same thing on the other graph as well. So let me mark this on both graphs, the half-lives. So after one half-life, we drop from 6 amps to what? What would be halfway from there? Yeah, we drop from 6 to 3. So at 22.2 seconds, we should be at, the current should be 3 amps. And then one half-life later, at 44.4 seconds, what's the new current going to be? Yeah, 1.5. We dropped to half of what it was. So 1.5 amps. Let me mark these. 6, 3, 1.5. And then one half-life beyond that, we drop to half of that, which would be how much? Half of 1.5 is going to be 0.75. So 0.75 amps of current. And then one half-life beyond that would be half of 0.75. So that's what, 0.375? So this gives us a variety of data points that we can use to graph a much more accurate curve. But we can take this even a step further. By using the time constant as well, we can get even more data points. But the difference I've noticed here, for half-life, the values are easy. You just take half of that, half of that, half of that. But the time values are kind of complicated because they've got this logarithm of 2 in them. On the other hand, for time constant, the time values are easy because it's just R times C. But the values of current or whatever are going to be more complicated because you're dividing by this irrational E value. So after one time constant, let me mark those on the graph as well. After one time constant, that's 32 seconds. So a little past 30. So we'll mark the time constant values in purple. 32 seconds, then 2 time constants. 2 times 30 would be 64. So something like this. 3 time constants would be 96. Something like that. And let's mark those on both graphs as well. Actually, I'll do that later. We'll fill that in afterwards. But every time constant, we should be taking the original amount and dividing by E. And for this one, I am going to need a calculator because E is not a nice, neat number. So we take 6, we divide by E. 6 divided by E. And I'm getting about 2.2. So at this time, we should expect 2.2 amps of current at that one time constant into the graph. And sometimes the times are even labeled as like tau, 2 tau, 3 tau. So you can label the time axis in units of tau, as if tau was a unit of time. Then after 2 time constants, we can take that value and divide by E. So 2.2 divided by E, or for even more accuracy, you can start with the 6. You're dividing by E and then dividing by E again. If you divide by E twice, what are you really dividing by? We could just write that in one step as 6 divided by what? If you're dividing by E and then dividing by E again, what are you really dividing by? The E's don't cancel out here though, because they're both in the denominator. Dividing by E is like multiplying by 1 over E. So what does the new denominator become? Yeah, you end up with 6 divided by e squared. So you could jump directly to 2 time constants, 2 tau, by taking the original amount and dividing by e squared. So 6 divided by e squared is about 0.81. So here we'll be at about 0.8. And then after 3 time constants, we can just take the original amount and divide by e cubed. 6 divided by e cubed is about 0.3. And note that these match up pretty well with the predictions we got from the half-life. One half-life, we're down to 3. After 1 time constant, a little bit later, we're down to 2.2. Then after 1 more half-life, we're down to 1.5. After 1 more time constant, we're down to 0.8. Then 1 more half-life, we're down to 0.75. So these all seem to fit a pretty good exponential decay curve. So by plotting those points, by marking the half-lives and the time constants, or really either one, you can do just the half-lives or just the time constants and get a pretty good graph. If you use both the half-lives and time constants, you can get even more accuracy. So that would be our graph for current versus time. Any questions on that so far? And then for the graph of charge versus time, we're going to need to do things a little differently. We can't just take 0 and take half of that, half of that, half of that, because that'll be 0 the whole time. But it's not decaying towards 0. What's this decaying towards? It starts at 0 and decays upwards towards what value? Yeah, it's decaying upwards towards 192. So instead of taking half the original amount, we should think of it as how far below the asymptote is it? Instead of thinking of this as 0, I would think of this as 192 below the asymptote. That's what we're taking half of. So what would be half of 192 below the asymptote? Half of 192 would be how much here? Yeah, 90 or 96, I think. So if we're 192 below the asymptote, half of that would be 96 below the asymptote. And 96 below 192 would be 98, I think. No, 96, right? So if we're 192 below the asymptote, we're going halfway towards the asymptote. So we'll be at 96. Because 96 is, again, what's decaying is the distance from the asymptote. We start off 192 below the asymptote. 1 half-life later, we're now 96 below the asymptote. That's half of 192. And then 1 half-life beyond that, we can just take negative 96 and take half of that. So half of 96 would be 48? 48, right? Half of 96. So that means 1 half-life later will only be 48 below the asymptote. So halfway towards the asymptote, negative 48. In other words, the actual value will be 48 below 192. So 48 below 192 would be 192 minus 48. That's 154. Is that right? 144. So that's 48 below the asymptote. And then after that, we take half of that distance. Half of negative 48 would just be negative 24. So 1 half-life further will only be 24 below the asymptote. So 192 minus 24 is going to be 172, 168. And then half of that will be only 12 below the asymptote. 192 minus 12 would be 180. So we can get all these data points, not by going halfway towards 0, but halfway towards the new asymptote. And then you could do the time constants the same way. After 1 time constant, we'll take the 192 below the asymptote and divide it by E. 192 divided by E will tell us how far below the asymptote we are after 1 time constant. So for instance, 192 divided by E is about 71. So 71 below the asymptote would be about 121. So after one time constant, we'll be at about 121. So you can put more and more points on this graph until you have enough to draw out a smooth exponential decay curve that goes through all those points. So this is a very quick way of getting lots and lots of accuracy on these exponential decay graphs. And then even if you don't have the equation, you can look at the points on the graph and predict with a pretty good accuracy what the amount will be at any time. If you do want to write out the equation, we can use that e to the negative t over RC idea. So let's try this. E to the negative t over RC. But we know what RC is. RC is 32 seconds, so we can actually fill that in. Negative t over 32 seconds. For the current graph, we know it starts at 6 amps, so we can just put a times 6 amps here. And also, what's the current decaying towards? Yeah, current's decaying towards 0. And that's exactly what this equation on its own would predict. As t gets larger and larger, e to a negative very large number gets closer and closer to 0. So we can use this equation for current. Current at any time is going to be 6 amps times e to the negative t over 32 seconds. That is e to the negative t over the time constant, r times c. For the charge graph, we can predict charge at any time. It's going to be slightly more complicated by the fact that it's not decaying towards 0, it's decaying towards some other value, 192. But we can still think of it the same way. We're still going to have the e to the negative t over 32. Seconds. But instead of that being the value, that's the amount that's decaying from the asymptote. So we should treat that e to the negative t over 32 as what's being subtracted from the asymptote. And we're also going to have some multiplier here, but it turns out that multiplier is not just the initial condition here, because we can't just have times 0. But since we're approaching the asymptote, I'm going to write this as 192, that's the asymptote, minus some exponential decay function. In the sense that we're getting closer and closer to the asymptote, the term that's decaying is how far below the asymptote we are. So I'm going to write this as minus. And we can actually even figure that out, that constant, by plugging in the initial conditions. We know that when t is 0, the charge is 0. And if you plug in 0 for t, what's e to the 0? Yeah, e to the 0 is 1. So if we plug in 0 for t, we get blank times 1. So 192 minus blank times 1 equals the charge at the beginning, which was in this case 0. So 0 equals 192 minus blank times 1. What does that blank have to be? What value in this blank will make this equation true? (192) minus what would be 0? Yeah, 192. So that's the multiplier here. So this would be our equation for charge at any time. It's still an exponential decay function, but it's got this constant value representing the asymptote. And generally, you'll have that asymptote plus or minus some constant times e to the negative t over RC. And to find that the plus or minus is going to depend on whether it's approaching from below or from above. But even if you can't figure out whether it's plus or minus, plug in the initial conditions. Like in this case, we plug in 0 for t and 0 for charge. Or more generally, 0 for t and whatever the initial value is. And then the only unknown left will be that unknown constant. So you can solve for that constant, fill it in, and you've got your exponential decay function. And at this point, we can now take any time you want and plug it in to find how much charge there is at that time. Plug in any time you want, find the amount of current at that time. And if you wanted to find voltages, you could just go back to the usual, for instance, for the voltage on the resistor, take this current times resistance, and that tells you the voltage of the resistor at any time. or take this charge divided by capacitance, and that tells you the voltage of the capacitor at any time. Any other questions on these functions or the graphs? All right, sounds good. Feel free to email me if you have any other questions, and I will see you next time. You're welcome.